All right. Sorry I missed you guys today. Home with well, the baby got sick, and then Grandma got sick, who watches him, and then my dad, Grandpa, got sick. It's wild. So we're passing it all to everybody, and we'll see how it goes. So far, I've come out relatively unscathed. We'll see how it works. Here's a little more in your notes about series. Now, we've done sequences. Now we're going to go into series. The only difference between a sequence, which is just a list of numbers separated by a comma, and a series is that it's not separated by commas anymore. We put plus signs in between them. We add them together. So a series is a sum of a sequence. And we use this sigma notation, Greek letter for S. And then the E sum. Yeah, E is silent in there. But we look for the sequence of partial sums. So sometimes what we do is we look at the pattern of maybe adding up a few of the terms to see maybe if it's going to add to something really big, maybe diverge, like infinity big, or if it's going to add to something finite, like some value, which would be convergence. And so we test for convergence and divergence a lot, pretty much the same way that we did our sum, or these types of things, like we did the integral from, a to some infinity 1 over x dx, and we knew that one diverged. You put in some a to infinity, as long as a is greater than 0, of 1 over x squared and dx, and we found out that it converged to some value, so it equaled something. Those are similar to what we're going to do with sequences, but slightly different, but in the same family. It's just we're getting them large and finding out that, hey, it actually adds to something rather than nothing that it seems like. All right, we're going to keep rolling. Get that out of here. Back, and there we go. Now we're ready for the real fun. So here's what a partial sum is like. What I'm going to do, we're going to do a sub n first. It says to do both. The sum S1 stands for sum of the first term in the sequence, so 1 over 1. You put 1 in for n. Tell me what you get, which is 1. S2 would mean adding the first two terms in the sequence, so that'd be 1 over 1 for n equals 1 and 1 over 2 for n equals 2. Add them together and we get 1 1/2, 3/2. And I think you get the pattern. S3, is the sum of the first three terms. Put them together. You can also just add the previous sum, just add 1/3, the new term to the previous sum of 3/2. That's fine as well. You get 11/6, and so on. We keep going. Here's S of 4. And it turns out, this is all well and good, there's that process on your calculator that is really helpful. If you use the sum sequence stuff I briefly showed you guys yesterday on your calculator, you can do these. Now, sum is under second list. That list function, you go over to math, there's a sum option, and then second list ops will give you the sequence, and then you can sum a sequence like we have here. So the sequence is the list of terms, and doing the sum of them, it'll add it all up. And you can get these totals. So we can use a calculator to evaluate a lot of these, but in general you can see a pattern as you go along. What's going to happen in this particular series, that is, if I add up all the terms in the sequence from 1 to n, in this case n equals 4, what's it going to do? Is it getting bigger? Is it going to converge to some number? On my calculator I put in S of 999 and it just got to something bigger. 25 over 12 is 2 point something. We're getting to 7.484. It just keeps growing. In this case, it's a lot like the integral of 1 over x. It diverges. This does as well. So you just keep growing and growing. So what we would say is this S sum. Now this is the summation notation. Check this out. I got it down here, and I'm going to highlight it for you. Sigma notation is you do a little e, sigma, and you start n equals 1 at the bottom. There is what you start with. Now we can start at n equals 0. We can start at any number, really. We tend to start at n equals 0 or n equals 1. Notice that starting at n equals 0 wouldn't be good in this case because we divide by 0. So we do n equals 1 to infinity of 1 over n. That means to sum up the digits, just like we did over there, and just keep going to infinity, it would diverge. You get an infinite area, or an infinite sum, I should say. It's not an area, it's a sum. And I will screw that up. I'll say area, and I mean sum, and things like that. But we're talking about series, which is summing up the terms in a sequence determined by the rule, like 1 over n. That's the story. Okay, keep rolling. We got to do I have to do 1 over b squared? So I think that there we go. This is 1 over n squared. Here's a partial sum for that, too. I'm kind of doing, isn't this kind of neat how I keep undoing and redoing? It's one of my special powers. Great. Here's the buttons, by the way, on your calculator, if you're wondering. I will help you with this when I get back, but I'm not going to do these by hand, and I don't have my calculator to flash up on the screen for you guys right now. But sum is under secondless math, sequence is under secondless ops, and you can actually sum up a sequence with this rule, kind of like we did yesterday. And it's fun because you can get to see what comes up. S of 1 is 1 over 1, S of 2 is 1 over 1 plus 1 over 2 squared, which is 4. So it's the first two terms added. And then this one's 1 over 1, 1 over 2 squared, 1 over 3 squared. And S of 99, I'm not going to write it out, but my calculator says 1.635. If I go to 999, a sum of the first 999 terms, I get 1.643. It is not growing by much in that big leap. This one converges. And this is just a means of using the partial sums to kind of see that. And we would say that this sum converges, 1 over n squared converges, kind of like the integral did. The sum of the series actually ends up converging to a number. It's like 1.6439. We're approximating here. Can we get the exact? Maybe, I don't know. But right now we're just looking at the idea that it does converge to some number, and we're just interested in that concept right now. So rolling right along. Next piece